Hi Liang. So to address the second part of your question, we're looking at theorem 4.2.6, which the long and short of it is, if we have a set of R vectors and a set of K vectors, the span of these two sets of vectors are equal to each other if and only if we can find a linear combination of the first R vectors to be equal to each and every one of the K other vectors, as well as taking a linear combination of the K vectors up the top. So we've got the K vectors to be equal to each and every one of our VI, which are each of those. So you'll notice these are all little scalar values, which is our definition of a linear combination. So a linear combination is if we take a set of vectors, multiply each of the vectors by a constant and add them up, that's a linear combination. So we can probably avoid paying too much attention to all this detail I've put over here, because we'll jump into exercise 22 and hopefully give a bit of feel for what's, I guess, largely a theoretical idea. All right, next slide. So question 22 says, is the span of the vector 1, 6, 4 and 2, 4, 1 and, or negative 1 and negative 1, 2, 5, is the span of those vectors equal to the span of these two vectors? And theorem 4.2.6 says if we can find a way to take a linear combination of our three vectors there to make them equal to each and every one of these vectors, and a linear combination of our vectors on the right there to be equal to each and every one of our vectors on the left, then we can say the span of what's on the left is equal to the span of what's on the right. So we can go ahead and work out values for our A's here to make them equal to this vector there and that vector there. And we can do that with a bit of matrix algebra. So that could be the columns of a matrix V, and then we could solve for a vector of the A's, making this what it's equal to on the right. But this is such a simple example, we can actually read off what the values should be. So here, if I was to say A was negative 1, A1 was to be negative 1, and A2 was to be 1, oops, I didn't write that in correctly, that should be 5, negative 5, and A3 was to be 0, we can go work out whether that linear combination of those three vectors with those specific scalar constants is actually equal to our vector on the right there. So negative 1 lots of 1 is negative 1 plus 2, so that's positive 1, so that's all okay. Notice I'm ignoring where there's the 0. Then if we go negative 1 times 6, that's negative 6 plus 4, so that should be negative 2, so that's all good. If we go negative 1 times 4 plus 1 times negative 1, that would make it negative 5, so that's all good as well. So we've shown that we can take a linear combination of these three vectors up here, and we've made it equal to that vector there. So we can repeat the same process to make these three vectors here equal to that vector there. So instead of solving for that, solve for that. So here, to give the game away, if we have A1 is equal to 1, A2 is equal to 0, and A3 equal to 1, we end up getting this vector here on the right, because we have 1 lot of 1 plus 0 plus 1 lot of negative 1, which equals 0, and I'll let you do the rest as an exercise. Then finally, to invoke this theorem properly, we have to do it in reverse. So we need to take a linear combination of these two vectors here and make them equal to that vector, and then do the same thing to make them equal to that vector and that vector. So another example, if we take b1 equal to 1, b2 equal to 1, we go 1 lot of 1 is 1, plus 1 lot of 0 is 0, so it's equal to 1, big tick. 1 times negative 2 is negative 2 plus 1 times 8, so 8 take 2 is 6, which I've drawn poorly there. And then finally, if we go 1 times negative 5 plus 1 times 9 is positive 4. So we've shown we can take a linear combination of these two vectors to get that vector. And then to really drag it out, the final steps are to make a linear combination equal to that vector, and then we've done all the possibilities to then invoke theorem 4.2.6. Alright, so I'll let you work out the final details, but hopefully that's given you a start on question 22 and a bit more of an understanding of theorem 4.2.6. Sorry, my tiny little screen got a bit messy. Okay, thank you.